Hello everybody and welcome to our video on power series. So now we start to really get into the big ideas that are behind why we've been so concerned with sequences and series. And so what we're going to talk about now is a power series, which is really a function that is expressed as a series. So the definition is a power series is a series of the form the sum from n equals 0 to infinity of c sub n times x to the n, which written out in long form is c naught plus c1x plus c2x squared plus c3x cubed plus ... The c sub n values are called the coefficients of the series, and x is a variable. So the power series is a function whose domain is the values of x for which the series converges. And in particular, it's a function that looks like an infinitely long polynomial, a polynomial with infinitely many terms. Okay, so definition, a power series centered at A is a series of the form the sum from n equals 0 to infinity of c sub n times x minus a to the nth power, which looks like c naught plus c1 times x minus a plus c2 times x minus a squared plus c3 times x minus a cubed plus ... This is also called a power series in x minus a or a power series about a. And the reason this is, in a nutshell, valuable is because when we center a power series at this term, we see that if I plug in a, all of the other terms cancel and we just get this 0th term left. So that means we'll know the exact value of the function at a, and that will allow us to figure out what the series looks like around that point. Okay, so we primarily are going to use the ratio and root test to find the domain for power series, but we're also going to need to check the endpoints of the domain using other convergence and divergence tests. So let's take a look at our first example. For what values of x is the series from n equals 0 to infinity of n factorial times x to the n convergent? So the first thing we're going to do is try to apply our ratio test. We take a sub n plus 1 over a sub n, take the absolute value. This gives us the absolute value of n plus 1 factorial times x to the n plus 1 over n factorial times x to the n power. So I split off from my n plus 1 factorial, just an n plus 1 term, times x to the n plus 1 times x. So I took that x to the n plus 1 as x to the n times x, all over n factorial times x to the n. And now we can do some simplification. X to the n cancels, n factorial cancels, and we get left with the absolute value of n plus 1 times x. Now, n plus 1 is strictly positive, so I don't need to write the absolute value around that factor, but the absolute value of x is not, so we'll keep the x in the absolute value. So now if I go to take this limit as n goes to infinity of the absolute value of a sub n plus 1 over the a sub n term, that's the limit as n goes to infinity of n plus 1 times the absolute value of x. Now, if I assume that x is not 0, so if we assume that x is not 0, then I can treat x like a constant since the variable for my limit is n, and I can pull the absolute value of x outside of the limit. Now, why does it matter that x is not 0? And that's just because this would then become the limit of 0 because 0 times anything is 0. So it would change the result here. So if we're assuming that x is not 0, then the limit as n goes to infinity of n plus 1. That's infinity. So it doesn't matter what I multiply it by, what x I multiply it by here, I get infinity. And so what does that tell us? Then that implies that the series diverges by the ratio test. Everywhere except x equals 0. Now we have to check what happens when x equals 0. So if x equals 0, then the series that we had here, which was the sum from n equals 0 to infinity of n factorial times x to the n, just becomes the sum from n equals 0 to infinity of 0, because if x is 0, we get 0 to the nth power. Though I actually should be a little bit more specific. It'll be n factorial times 0 to the nth power. And this will be 0 everywhere except for the n equals 0 term. So when n equals 0, we get 0 factorial times 0 to the 0 power plus n equals 1, which should be 1 factorial times 0 to the first power plus blah, 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 blah. And so what do we get? 0 factorial times 0 to the 0 power is 1. Now, that's a little weird, but it's a definitional issue. So we mentioned briefly in a previous video, I believe, that in a series, we treat 0 to the 0 as being equal to 1, even though, in general, 0 to the 0 is undefined. So why do we do this? Well, like we saw earlier, what we're trying to describe with the power series is this infinite polynomial, and the first term of an infinite polynomial is always a constant, not a constant times x to some power. So since we want to make sure that the first term of our power series is always a constant, we choose to make a sort of notational exception for power series and say, hey, whenever we're talking about a power series, what we mean when we say 0 to the 0 is actually 1, because we want that first term of our polynomial to be the appropriate constant. Okay, so with that being said, all the other terms, 0 to the first power, to the second power, etc., those terms will all be 0. So we can actually evaluate this sum, its exact value, when x is equal to 0, which means that the series converges at x equals 1. But not only at x equals 1, at only x equals 1, because we already showed that it diverged everywhere else. Or sorry, I said x equals 1 at x equals 0 when the series is equal to 1. Okay, so let's go ahead and dig into some more examples here. There's a whole lot of these kinds of problems to deal with. For this next one, for what values of x is the series convergent? We've got the sum from n equals 1 to infinity of the absolute value, or of x minus 4 to the nth power over n. So I'm going to take the absolute value of a sub n plus 1 over a sub n. So we're just doing our ratio test over and over and over and over again. So what do we get? X minus 4 to the n plus 1 power over n plus 1 divided by x minus 4 to the nth power over n. That's the absolute value of x minus 4 to the n plus 1 power over n plus 1 times the reciprocal, n over x minus 4 to the nth power. And now we'll simplify that a little bit. We get the absolute value of x minus 4 times. So I canceled the n factors of x minus 4. And then what do I have left? I have n over n plus 1 here. And I can, I know that n over n plus 1 is positive, so I can pull that out of the absolute value and just leave the absolute value of x minus 4 inside. So now when I go to take the limit as n goes to infinity of my absolute value of a sub n plus 1 over a sub n, this is really just the limit as n goes to infinity of n over n plus 1 times the absolute value of x minus 4. And since x is treated as a constant with respect to this limit whose variable is n, we can pull the absolute value of x minus 4 outside of the limit. And we get this limit. And this limit, I'm going to skip writing out all the computation because we've done so many of these at this point that you know that that limit is going to be 1. So now if I want to apply the ratio test, well, the ratio test needs to check when the result of this limit is less than 1, right? This is what we're checking for, the ratio test condition. So I need to solve that inequality. So the series converges when the absolute value of x minus 4 is less than 1, which implies that x minus 4 is between 1 and negative 1. And if I add 4 to both sides, I get that x is between 3 and 5. And so there, I have an interval for which the series is convergent. But I don't have the final interval because I don't know if this thing converges at 3 or 5. Notice, what's going to always happen with this situation is when you apply your ratio test, the values on the endpoint, when you plug them back in over here to your ratio test, will always give you 1. So if I plug in 5, I get 5 minus 4 is 1. If I plug in 3, I get 3 minus 4 is negative 1. Take the absolute value, it's still 1. So on these endpoints, the ratio test will always be inconclusive. So we must always need to check convergence at the endpoints when using the ratio test. Now, in the first example, we got that the thing converged everywhere except for one point. So we had no interval. We didn't have to check endpoints there. But here, we've got an interval. We've got to check these endpoints. So what we're going to do is take x equal to 3 and actually plug it back into the series, right? So if we go up here, I'll just put a little box around the series. I'm going to call the whole series star here, since I'm going to have to rewrite that once or twice. So star is the series of x minus 4 to the n over n. So this becomes the series, so star becomes the series of 3 minus 4 to the n over n. Which is the sum from n equals 1 to infinity of negative 1 to the n over n. And we know that this converges by the alternating series test, and see previous video. And I'm not going to redo that work here since we've already done that, but I would certainly expect if I asked a question like this on the test, I would expect the student to show the alternating series test. But for time on the video, since you already have a video that's got that exact alternating series test problem on it, I'll just go ahead and skip that part here to cut down a little bit on the time. So now we know that this series converges when x equals 3. What about at the other endpoint of my interval, x equals 5? What do we get? We get the sum from n equals 1 to infinity of 1 to the nth power, so that's 5 minus 4 to the nth power over n. 5 minus 4 is 1. 1 to any power is still 1. So this is 1 over n. And this diverges because it's the harmonic series. And we've already proven that one. So finally, star, the series we're concerned with, has the interval of convergence 3 is less than or equal to x is less than 5. Or I should say, instead of has that as an interval converge, we'll say converges on the interval from 3 to 5, including 3, but not including 5. Okay. So that's it for that one. Now let's go ahead and take a look at another example. So example 3 here, for what values of x is the Bessel function of order 0 defined below convergent? So this function's notated j naught of x, and it's equal to the series from n equals 0 to infinity of negative 1 to the nth power times x to the 2n over 2 to the 2n times n factorial to the second power. Okay, so that's a kind of a whole lot there. One thing I'm going to do that will reduce the complexity here of this is I'm going to rewrite it a little bit. The sum from n equals 0 to infinity of negative 1 to the n times, and since x to the 2n and 2 to the 2n have the same power, I can write that as x over 2 to the 2n, and this is over n factorial, and instead of writing n factorial squared, I'm just going to write n factorial times n factorial. I think that will make it a little easier to see what's happening in the next step. So now I set up my ratio, a sub n plus 1 over a sub n. Negative 1 to the n plus 1 times x over 2 to the 2 times parentheses n plus 1. Be careful about that. Anywhere you've got an n, you've got to replace that n with n plus 1. That means if there's a multiplication or an exponent or anything like that, you need to put a parentheses around that. And so down here I've got n factorial times n factorial, so it becomes n plus 1 factorial times n plus 1 factorial, all over negative 1 to the n times x over 2 to the 2n over n factorial times n factorial. Sounds a little bit of a mess, but that's okay. We're going to simplify it a little bit further, and we're also going to change this from division to multiplying by the reciprocal. The first thing I'm going to do is distribute that 2 times the n plus 1 and get 2n plus 2. And I'm also going to rewrite my n plus 1 factorials as n plus 1 times n factorial, n plus 1 times n factorial, times, and then I'm flipping this denominator, so I get n factorial times n factorial over negative 1 to the n times x over 2 to the 2n power. And now we can do a whole bunch of cancellation. So -1 to the n plus 1 power over -1 to the n just leaves me with -1 to the first power. N factorials cancel each other. And then up here we've got x over 2 to the 2n plus 2. And down here we've got x over 2 to the 2n power. So I can cancel 2n factors of that expression. And now let's see what we've got left. -1 times x over 2 squared times, and then all I've got left is 1 over n plus 1 times 1 over n plus 1, which is 1 over n plus 1 squared. So the absolute value of -1 is 1. And x over 2 squared, take the absolute value, it's already positive. So we can just write this as x squared over 4 times, and the absolute value of 1 over n plus 1 squared is also strictly positive. So that's 1 over n plus 1 squared. So now I can set up my limit. Got x squared over 4 times 1 over n plus 1 squared. And this limit treats x squared over 4 as a constant. So we pull the x squared over 4 out. And that limit is 0. So this is x squared over 4 times 0. And that's 0, which is less than 1. So this implies the series converges no matter what value x is. So for all x. All right, no matter what x I had there, I'm going to end up multiplying by 0. So I'm going to get 0. So this whole thing is going to converge no matter what value of x is. So in other words, it converges on the interval from -infinity to infinity. So let's go ahead and summarize what we've got so far. So one little addition, the radius of conversion, so a little definition, the radius of convergence is the largest number r such that the power series converges on the interval a minus r to a plus r. R is also the number when you get the absolute value of x minus a is less than r. When you get to that expression, r is that radius. So let me illustrate real quick by going back to one of our earlier problems. So this one, where we had an interval. So up here we had the absolute value of x minus 4 is less than 1. So if I'll write that in red here, we say the absolute value of x minus 4 is less than r. That's the radius of convergence. And the reason we call it the radius of convergence is because if we draw this interval from 3 to 5, the center of our power series was at 4. So this is the center. And the distance out from the center is the radius, which is 1. So back to here. Let's take a look at a summary of the examples we've seen so far. So in this first example we saw in a previous section, so the sum from n equals 1 to infinity of x to the n minus 1, which acts like a geometric series, but we often write as the sum from n equals 0 to infinity of x to the n. And we saw that this series converged only from -1 to 1, not including the endpoints, which means the radius of convergence is 1. Now the sum from n equals 0 to infinity of n factorial times x to the n power, we found that that converged on a radius of length 0 because it only converged at the point 0. So if I have an interval, or if I have a series that only converges at a single point, there is no distance away from that it converges. So in that case, we say the radius of convergence is 0. Now, we already went over this example. N equals 0 to infinity of x minus 4 to the n over n. The radius of convergence was 1. The interval of convergence was from 3 to 5. And here, we've got the sum from n equals 0 to infinity of negative 1 to the n times x to the 2n over 2 to the 2n times n factorial squared. The radius of convergence is infinity for that, and the interval of convergence is negative infinity to infinity. So the key thing that I want you to understand is that this really covers all of the situations. You can have intervals where both ends are open or both ends are closed. You can have intervals where one is open and closed. You can have intervals that are only convergent at a single point. Or you can have intervals from negative infinity to infinity. And so we summarize this in the following theorem. Call this the convergence of a power series theorem. And it says that for a given power series of the form n equals 0 to infinity of c sub n times x minus a to the n, there are only 3 possibilities. First, the series converges only when x is equal to a. Second, the series converges for all x. Or third, there's a positive number r, the radius of convergence, such that the series converges whenever the absolute value of x minus a is less than r, and diverges whenever the absolute value of x minus a is greater than r. That is, the series converges on the interval a minus r to a plus r, and may or may not converge at the endpoints. Okay. So with that out of the way, let's go ahead and take a look at just a couple more examples. So find the radius of convergence and the interval of convergence for the sum from n equals 0 to infinity of negative 2 to the n times x to the n over the square root of n plus 2. Okay, we'll start out with our ratio test. We've got to write out our a sub n plus 1 over a sub n terms. And I'm going to go a little bit quick through this now because we've done so many examples of this ratio test at this point that I'm hoping that everybody can follow along even when I go a little faster. And of course, I'm sure there are some people right now thinking, I wish he would always go faster. But I try to keep an even-keeled pace. All right, now I'm going to multiply by the reciprocal, so I get negative 2 to the n plus 1 times x to the n plus 1 over the square root of n plus 3 times the square root of n plus 2 over negative 2 to the n times x to the n, absolute value. And now we simplify. Negative 2 to the n plus 1 over negative 2 to the n is just negative 2. X to the n plus 1 over x to the n is just x. And since I've got the square root on top and bottom here, I could combine those square roots into 1. It's n plus 2 over n plus 3. The absolute value of negative 2 is 2. We don't know if x is positive or negative, so we have to leave it in the absolute value symbol. And this square root is certainly positive. So now I can compute my limit. So my limit as n goes to infinity of this thing, it's going to look like the following. 2 times the absolute value of x times the limit as n goes to infinity of this square root. And the square root is a continuous function, so I can always move my limit inside of that function. So this becomes the square root of the limit as n goes to infinity of n plus 2 over n plus 3. And this limit, we've done a bunch of these, and you know that this limit is 1. So this is 2 times the absolute value of x times 1. Now, the condition for the ratio test is that this thing needs to be less than 1 for this to converge. So that tells me the series converges, and we'll just go ahead and denote this series star like we did before. The series converges when 2 times the absolute value of x is less than 1. So we'll divide by the 2. We get the absolute value of x is less than 1/2. And now we're in that form. The absolute value of x minus a is less than r, a being 0 in this case. And so this is my r. That's the radius of convergence. But now to find the interval of convergence, I have to do a bit more work. Since the absolute value of x is less than 1/2, that implies x is between -1/2 and a +1/2. And now I always have to check the endpoints. So when x equals -1/2, let's see what happens to our series. So we've got -2 to the n times x to the n over the square root of n plus 2. That was n plus 2, right? Yep. Bugging out on the drawing a little bit. Come on, Word, work with me here. Square root of n plus 2. There we go. And now, what do I see here? Well, these are both to the nth power, so I can combine those two together. And -2 times -1/2 is a +1. So that's actually just the sum from n equals 0 to infinity of 1 over the square root of n plus 2. And if I look at 1 over the square root of n plus 2, how does this compare to 1 over the square root of n? Well, I've got a larger number here in the denominator, so that means this is smaller than 1 over the square root of n. But the series 1 over n to the 1/2 power diverges by the p-series test. So this inequality is the wrong one. Doesn't help me. So in order to show that this thing converges, I have to use the limit comparison test. Or diverges, I should say. So we got to use the limit comparison test. And, well, how are we going to do that? We set up the limit as n goes to infinity. We take one of our terms, say 1 over the square root of n plus 2. Divide it by the term for the other series we're comparing it to. This becomes the limit as n goes to infinity of the square root of n over the square root of n plus 2, and I can move that all into one square root. And I can move that limit inside that square root. And that limit is going to be 1. So what does that tell us? This is positive and finite. So both series diverge. All right, we already knew that 1 over n to the 1/2 power diverges by the p-series test, so this one also diverges by the limit comparison test. Okay, now we've got to try x equals +1/2, our other endpoint. And when we plug that into the series, we'll get something pretty similar the sum from n equals 0 to infinity of negative 2 to the n times 1/2 to the n over the square root of n plus 2. Now again, I can multiply these together because the exponents are the same, and negative 2 times 1/2 is negative 1. So this becomes the sum from n equals 0 to infinity of negative 1 to the n over the square root of n plus 2. Now if we take a look at the b sub n here, this is an alternating series. So b sub n is 1 over the square root of n plus 2. And so b sub n plus 1 is 1 over the square root of n plus 1 plus 2, which is the square root of n plus 3. So b sub n is bigger, b sub n plus 1 is smaller, so it's decreasing. And of course, the limit of this thing is obviously 0. So that implies the series converges by the alternating series test. So we have divergence on x equals negative 1/2 and convergence on x equals 1/2. So the interval of convergence then is negative 1/2 non-inclusive to 1/2 inclusive. Okay, now we've done quite a few of these. We're going to do one more example, but one thing that I hope is coming through in this is that in order to deal with these power series, you really need all of the skills that you developed in checking the convergence of series from the previous sections. You need to know your geometric series theorem, your comparison theorems, your limit comparison theorems. This section really requires that you tie all of those skills together into one. All right, so let's take a look at our last example for this section. I gave myself, I guess, more room than I really needed. That's okay, not a bad thing. Let's go ahead and dig into this last one. Find the radius of convergence and the interval of convergence for the sum from n equals 0 to infinity of n times x plus 3 to the nth power over 4 to the n plus 1th power. Okay, a sub n plus 1 over a sub n. So again, at this point, we've done a bunch of these, so I'm going to write this out really quickly. 4 to the n plus 1 is 4 to the n plus 2 over n times x plus 3 to the n over 4 to the n plus 1. And I'm going to kind of skip some of the simplification here as well. Got n plus 1 over n. I'll just write that together. X plus 3 to the n plus 1. When I multiply by the reciprocal, I cancel out n factors of that, and I get x plus 3. And in the denominator, when I flip this over, I cancel all of the 4s except for one of them. And so that's my simplified form for the expression. And n plus 1 over 4n is all positive, so I can pull that out of the absolute value, and I get left with the absolute value of x plus 3. And now I can go ahead and dive into taking my limit as n goes to infinity. That's the absolute value of x plus 3 times the limit as n goes to infinity of n plus 1 over 4n. And again, I'm skipping those really simple limits here. That's going to be 1/4 for that limit. And of course, our condition for the ratio test is that this converges when the whole thing is less than 1. So this implies that the absolute value of x plus 3 has to be less than 4. And of course, now this is our absolute value of x minus a is less than r. So r is 4. That's our radius of convergence. As for the interval, we get x plus 3 has to be between 4 and negative 4. And if I add 3 to each side, I get x is between 7 and negative 1. So now we have to check endpoints. We can plug in x equals negative 7. So that's going to give me a negative 4 to the n. So n times negative 4 to the n over. And let's make sure I copy this down right this time. 4 to the n plus 1. Okay, so this becomes the sum from n equals 0 to infinity of n times negative 1 to the nth power times 4 to the nth power over 4 to the n plus 1. And in this case, I can cancel that. I get left with a 4 in the denominator. And we end up taking a very similar approach here because we take the limit as n goes to infinity of n over 4. Right, this is my positive portion. I'm ignoring the alternating portion. That's infinity. So the series diverges by the test for divergence. Okay, now we'll check when x is, that should be positive 1. Now, when I plug in a positive 1 into the series, I'll get 4 to the n here. So this becomes the sum of n times 4 to the n over 4 to the n plus 1. And that simplifies to the sum from n equals 0 to infinity of n over 4. And again, we take the limit of those terms. We get infinity, and that implies the series diverges by the test for divergence. So that means our final interval, our interval of convergence, is given by x between 1 and negative 7. All right. Well, that's it for that one. Thank you for watching.